The hydrosphere isn't just liquid water, it also includes the cryosphere, or the frozen water on Earth, the glaciers, ice sheets, and permafrost. And the ice? Well, the ice is melting. Let's begin with a demonstration of albedo, which is the proportion of light that is reflected by a surface. Having a high albedo means a surface is very reflective and doesn't absorb much light. A low albedo means the surface is generally dark and absorbs a lot of light. In this experiment, you will see two different surfaces: a reflective piece of aluminum, which has a high albedo, and a dark piece of cloth, which has a low albedo. I'll be using a temperature probe to measure the temperature of the air just above each surface. So here I've got an experiment set up where I have a reflective piece of foil and a dark piece of fiber um, with a temperature probe above it. Now you may notice that my left temperature probe here is set up next to my tinfoil, and the right temperature probe is set up next to the dark cloth. Look at the temperature difference. Let's keep this phenomena in mind as we venture into the Arctic. Kitty here doesn't go to the Arctic. No, Kitty here doesn't like the cold. Go away. Because global temperatures are increasing, the rate at which the ice is melting is increasing. But there's a feedback cycle happening here. Below the ice is, well, bedrock. And as the ice melts, more bedrock becomes exposed. And because the bedrock has a low albedo, the temperature increases faster, which melts more ice, which exposes more bedrock, which melts more ice, so on and so forth. This feedback cycle has resulted in the polar regions of Earth warming at a faster rate than the rest of the planet. All this melting has reduced the size of glaciers by quite a bit. Now, a glacier is best defined as a moving river of ice that forms on mountains and near the poles. This is different from sea ice, which is just, well, frozen seawater. Arctic sea ice has seen a sharp decline. In 2016, the Arctic sea ice was 700,000 square miles less than the historical average. This change is visible from space. Another effect of melting ice is the release of gases trapped in the ice, which introduces yet another feedback cycle. As the ice melts, it releases more gases which contribute to warming. Methane released from the melting of ice has substantially increased since the 1980s and is currently responsible for 0.2% of all methane emissions. Now, 0.2% doesn't sound like a lot, but that's 17 million tons of methane every year. All this ice, when it melts, flows into the oceans. Cumulatively, the world's oceans have risen by 10 inches since the 1800s as a result of this ice melt. This rise in sea level has increased the number of flood days in coastal cities, which has an economic impact on these areas, but also a health impact as the high water levels spread pollutants, especially wastewater that may contain harmful bacteria throughout coastal cities. This map shows the amount of land converted to, well, open water ocean along the Atlantic coast through 2011, the most recent year we have data. This encroachment of ocean on the land may lead to the displacement of people farther away from the coast. The melting of sea ice and increasing temperatures causing changes to ocean circulation. You see, the currents in the ocean, or the way water flows throughout the planet, is slowing down. These ocean currents spread out the temperature of the ocean, bringing warmer water to the Arctic regions where it loses heat before coming back down into the tropical region. As these currents slow down, more oceanic heat will be retained near the tropics. And it's the heat of the ocean that creates cyclone storms like hurricanes. This has been hypothesized to increase the severity of storms, especially hurricanes. While the number of storms hasn't changed by much, the frequency of severe hurricanes has increased. So we may not see more hurricanes, but the number of hurricanes we see that are categorized as severe, so category 4 or 5, may very well become higher. The overall temperature of the ocean is increasing as well. The overall sea surface temperature has increased by about 1 degree Fahrenheit above the historical average. And the total heat energy absorbed by the whole ocean, so not just the surface, has also increased. This increase in ocean temperature has been causing damage to marine wildlife because many fish that live in colder waters are adapted to dealing with, well, cold water. The excess heat is causing metabolic stress. All this combined with warm water holding less oxygen, we expect to see either a decline in fish populations or a shift in their natural range. Fish that survive in warm waters are also struggling and are also moving farther in towards, well, farther north in southern latitudes where the waters may not be quite as warm. One of the largest threats of ocean warming is the bleaching of coral reefs. For reasons we don't fully understand, when the water is too warm, corals will kick out the algae that they otherwise have a symbiotic relationship with. It's also where they get all their pretty colors from. Now, coral reefs support about 25% of all marine biodiversity, and all of that is dependent on this symbiosis between corals and the algae. When coral bleaching occurs, the biodiversity in coral reefs plummets, and well, some reef ecosystems have recovered from a bleaching effect, but quite a few have not. Warming is not the only thing that can cause coral bleaching. Ocean acidification can too. Now, the ocean is a large carbon sink, and while the majority of the carbon dioxide absorbed in the ocean is due to photosynthesis of algae and phytoplankton, an increasing amount of this carbon dioxide is just being dissolved into the water. Now, because humans continue to pump more carbon dioxide into the air, and with deforestation reducing the capacity of terrestrial ecosystems to act as carbon sinks, all this additional oceanic carbon dioxide cannot be immediately used by photosynthesizers in the ocean. This dissolved carbon dioxide reacts with water molecules to form carbonic acid, which is causing ocean acidification. This causes coral reefs problems because the actual structure of the reefs, as produced by the coral animals, is calcium carbonate, which you might know of as chalk. And I'm sure we've all seen this reaction before. When any carbonate, like chalk, comes into contact with an acidic solution, it begins to dissolve. This makes it harder for corals to produce their shells. And it is also making it difficult for most shellfish in the ocean to maintain their shells, well, too. The oceans are the source of 2/3 of all the oxygen we breathe. Economically, we rely on it for food and tourism, recreation. These changes to the ocean between acidification, warming, which causes a decline in coral reefs and the fish they rely on, and the increasing severity of storms and sea level rise threatening coastal cities, we really need to consider how we're doing things here. The general thought in environmental science is the world will adjust, chemistry will persist, evolution will continue, and the planet will be fine. It'll look different, but it'll be okay. The question is, will humans be okay? Will we adjust to a changing planet? Or will Homo sapiens just be the next species to meet the same fate as the other human species? Now, between Homo erectus, Homo neanderthalis, Homo habilis all being extinct, we're the only humans remaining. For now.